Hi guys, in today's video we're going to be talking about limits, and limits are going to be really important for our exploration of differentiation. A limit is the value a function gets closer and closer to as we approach a particular value of the independent variable. Limits are written as is shown here, and they're read as the limit of f of x as x approaches a. Now let's look at an example. Here we have the limit of 3x plus 4 as x approaches 2. This is known as a two-sided limit, and we evaluate it by considering each of the one-sided limits. Our first one-sided limit is the limit of 3x plus 4 as x approaches 2 from the positive side. So we draw ourselves a table and we start considering values that are close to 2 and getting closer. So I've chosen the values 3, 2.5, 2.1, 2.01 and 2.001. Each of these values is on the positive side of 2 and is getting closer and closer to 2, so we are approaching that value 2. We now evaluate our function at each of those points, and we get the values 13, 11.5, 10.3, 10.03, and 10.003. What we see here is that as our value gets closer and closer to being 2, the value of the function gets closer and closer to being 10. So we would say that the limit of the function 3x plus 4 as x approaches 2 from the positive side is 10. And then we can consider our opposite limit. So we'll have the limit as x approaches 2 from the negative side of the function 3x plus 4. So we've drawn another table, and this time we're considering values that start at 1 and approach 2. So we've got 1, 1.5, 1.9, 1.99, and 1.999. And again, we'll evaluate each of those. And we get the answers 7, 8.5, 9.7, 9.97, and 9.997. And in a similar way to last time, we can see that as the value of x gets closer and closer to 2, the value of our limit is getting closer and closer to 10. Now, since the limits on both sides of the approach, so the two one-sided limits have the same value, this means that our two-sided limit has that value 10. And this is a really important point. You can only define the two-sided limit, the limit as x approaches 2, if the two one-sided limits both end up with the same value. And that is not always the case, as we'll see in a moment. For any rational function that is defined at x equals a, the limit of that function as x approaches a is just given by the value of the function at that point. So in our previous example, the limit of 3x plus 4 as x approaches 2 could have been evaluated simply as 3 times 2 plus 4 equals 10. This is actually a fairly trivial result because you would normally not use limits in these circumstances. But if you are asked to find the limit of a well-behaved function that is defined at the point you're after, simply substitute the number. We'll now take a look at another example that's not quite so well-behaved. We have here the limit of 3x squared divided by x minus 2 as x approaches 2. And we can immediately see a problem, because when x equals 2, the denominator of this quotient is 0, and we cannot have something divided by 0. So again, we break it into our two one-sided limits, approaching 2 from the positive and the negative side. Again, we draw our table of values, and we pick values of x greater than 2 that are progressively getting closer and closer. And when we evaluate the function at each of these points this time, what we see is instead of the values getting closer and closer to one particular value, they're just getting larger and larger, each time by about a factor of 10. And what that tells us is that as we pick values that are closer and closer to 2, our function is going to continue getting larger and larger. And in fact, the limit as x approaches 2 from the positive side is actually infinite. When we do the same thing for the other limit as x approaches 2 from the negative side, we get completely different answers. Now we have negative values that are in the same way getting larger and larger. So again, our limit is approaching infinity, but this time it's negative infinity. Now this leaves us with the case that the limit from the positive side and the limit from the negative side, the two one-sided limits, are not the same value, which means that our two-sided limit is not defined. What we're dealing with here is a form of asymptote that we have seen previously, where our function actually looks like this. It has a vertical asymptote and another vertical asymptote at the same value. So at the point x equals 2, the function does not exist. And if you approach it from the negative side, you end up at infinitely large negative values. But if you approach it from the positive side, you get the opposite. You get infinitely large positive values. So the limit is not defined for x approaches 2. We'll take a look at one last example, and that's the limit of x squared minus 1 divided by x minus 1 as x approaches 1. We consider both of the one-sided limits, draw up our table of values, choose the values that we wish to evaluate at, and evaluate our function. And what we see in this case is that as we approach x equals 1 from the positive side, our values get closer and closer to 2. And as we approach x equals 1 from the negative side, our values also approach 2. So this is a case of a function that has a well-behaved limit equal to 2, even though the function itself does not work at x equals 1. So we get 1 squared minus 1 is 0, divided by 1 minus 1 is 0. 0 divided by 0 means that that function is not defined at x equals 1, but everywhere else it is, and it's actually a straight line. And so that function, as you approach 1 from either side, approaches the value 2, even though it does not actually have the value 2 at x equals 1.